is in John Martin Navales. Are they from NIE as well, Jingyu? You are all, to all participants, just a small note to you that this event is a part of a WAM seminar series co-hosted by AIT faculty, including myself. So the event currently is a monthly event, which will be broadcasted live on Facebook after this announcement. Later on, the recorded seminar will also be shared on our WAM Facebook page. Momentarily, I shared the WAM introductory promotional video, so we have a YouTube channel to share all of those. So with that, I encourage all participants to go ahead and then share this Facebook live stream on your Facebook page so that the scientific discussions taking place here can reach out to more participants. Okay, so with that, I will start the Facebook Live now. So give me a moment. Okay. Okay, so welcome everyone to today's seminar. Let me first start to share my screen to introduce to everyone our today's presenter. So I'm very happy to have been able to invite Dr. Jingyu Wang, Assistant Professor from National Institute of Education, Autonomous Institute of Nanyang Technological University, one of the top universities in Asia and also globally recognized. So Dr. Wang will be sharing with us his talk on mesoscale convective systems from aircraft in-situ observation to global model simulation. So Dr. Wang is currently assistant professor at NIE. He's an observationalist who uses aircraft in-situ measurements to explore the microphysical properties of cloud and precipitation of convective systems. I found the topic very relevant to our AIT, or more specifically, water engineering and management program. So that's why I have initiated the invitation to Dr. Wang. So with this, I will stop sharing now and return the floor back to Dr. Wang. Please, Jingyu, the floor is yours. Thank you.
Thank you, Josh, for the introduction and the invitation. It's my great honor to be here to share with you some of my research related to Southeast Asia. So today's topic is the mesoscale convective system from aircraft in-situ observation to the global model simulation. First, let me reintroduce myself. My name is Jingyu Wang. I'm currently an assistant professor at NIE NTU, and I joined the board this January. Before that, I worked as a postdoc and a data scientist at the Pacific Northwest National Lab in the United States. And here is a brief my educational background and research focus. I received a bachelor degree from Nanjing Institute of Meteorology with a major in remote sensing. So during my undergraduate study, I learned to use a satellite to observe the weather and the climate phenomena from the space downward. And upon graduation, I continued my education with a master's degree in atmospheric science. But I switched my topical study from the remote sensing to the ground-based observation because I have a background in EE. So I designed and collaborated multiple ground-based atmospheric sensors, for example, the wind gauge, diffractometers, microwave radiometers, and surface-based radar that's shown here. And then I pursued a PhD degree in the United States from University of Arizona with a major in atmospheric science and a minor in hydrology. And this time, I switched my platform again. So different from the satellite sensors from the space looking downward, or from the ground-based observation looking at the weather phenomenon upward. I did my research. I flew the aircraft in between the cloud top layer and the surface and do the aircraft in-situ measurements of cloud properties, including the water content, particle size distribution, and this is the aircraft MLA used. Upon graduation, with 2 PhDs, I continued to work as the postdoc and the research scientist at the Pacific Northwest National Lab in the United States. And I put what I observed from the multiple platforms to the modeling system. I was trying to improve the model prediction of the mesoscale convective system. And this year, I moved to Singapore, joined the NIE NPU, and I switched my study focus, but also still on the modeling part. But the modeling region switched from the continental United States to the Southeast Asia. So here is when I was serving my quarantine in the hotel, 2 major things happened. One is the Malaysia flood. That's one thing in 120 years. So I'm still modeling this event. And another thing was the historical record-breaking heatwave events in India. So I will share some information and experience later. So what I have oh, sorry, it's not for me. Okay. So why do we care about the mesoscale convective system? So we will call it MCS for short. So the MCS is of great importance to regulate the global and regional atmospheric circulation, hydrological cycle, radiation budget, and energy cycle. So it produces a majority of the precipitation all over the world. So over Southeast Asia, we receive the precipitation a lot, but more than 60% of the precipitation comes from those large cloud systems, MCS. So we can have a multiple platform to do the observation as shown here, satellite, and also the ground-based observation. But what I really care is what's inside the cloud system, because it's difficult for you to approach there. So unless you can stand there and hold the instrument and do it. That's the reason I use the aircraft to fly into those systems and do the in-cloud sampling and to obtain the first-hand information of the cloud microphysical properties and the relative properties. With the information retrieved from the aircraft in situ measurements, I want to apply the parameterization scheme into the model, not regionally, but globally. So I need to know how the MCS systems, they evolve from initiation to upscale growth, dumping the majority of the precipitation and then disappear during the dissipation stage. And the tracking of the MCS system is really critical for the majority of the world, because the United States is well covered with dense radar and satellite observation network. However, such network is missing in the majority of the world, for example, in Africa and also in our Southeast Asia. So the entire domain is covered more than 50% of the ocean. So we cannot deploy a permanent island to deploy a radar in the middle of the ocean. So the global tracking of MCS is critical for us. So here is a brief outline of this talk. First, I will show how to use aircraft in situ measurements to collect the MCS inside information regarding the microphysical and radiative properties. And then I want to introduce you the global scale detection and tracking of MCS. And lastly, based on the information we collected, we want to improve the simulation of the MCS, either from the regional climate model or the global climate model. And also, I will introduce some work that I recently embarked here over Southeast Asia. Let's start with the first topic, the aircraft in situ measurements. 1 second. Not for me. So here is the research aircraft I mainly used back in the States during my PhD study. It's called the Citation 2 research aircraft. So do you have any idea why it's called Citation 2? Why it's ranked number 2? Because the aircraft cloud penetration field experiment is extremely dangerous. So the first Citation 1 aircraft crashed during the campaign. So we bought another one. And here is the deployment of the field campaign that I'm involved in my PhD. So you can see you have the vertical pointing radar, a wind profiler, scanning radars, and also the surface-based ring gauge. So when a system overpasses the study region, we will have this Citation 2 aircraft fly, penetrate through the cloud system doing the in-cloud sampling. And meanwhile, we have a NASA ER2 research aircraft fly above the cloud and mimic the observation of the satellite. So in this way, the cloud is transparent to us. So every single detail is reviewed from this intense observational network. And here is the example of the Citation 2 research aircraft's trajectory. So you can see we start from a dark color and then we move to warm color as a time lapse. So it did a lot of different flight patterns like a zigzag and spiral. And on the right-hand side, it's a 3D, it's a 2D animation of the aircraft trajectory. So in the middle is 3D, but it's a fixed domain snapshot. Here is a 2D. So the green color represents the stratiform ring area, which is very stratified and safe to fly. However, the red color represents the convective core. That means you will experience strong updraft and downdraft. So you see that for sometimes the aircraft that's touched a little bit of the convective core region, strongest updraft. So that's, I can assure you, want to experience. Because think about this, the aircraft speed is like 100 meters per second, but when you approach the core region of the convective system, the vertical motion is like more than 10 meters per second. You are like bumping severely. So I still remember my first flight was I threw up like crazy. So using the aircraft instruments, those are the detailed list of the aircraft instruments. We can measure. Sorry, I have some background noise because construction is taking place. So there are several types of the aircraft instruments for the measurement of the particle size distribution. So here you can see they are marked with red colors. Those are called the optical array probes. They are responsible for the measurement of particle size distribution. So for those probes, we have two arms basically. One arm is the laser, and one arm receives the laser. So when the aircraft flies through the cloud and it encounters hydrometers, for example, the ice crystals, cloud droplets, or aggregates, the laser beam will have some shadow left by those hydrometers, and we record the shadows into those beams. And also there are other type of instruments, not called optical array probes, it's called the CCD cameras. So it takes in situ high resolution picture of the cloud particles. So we try to convert those the shadow image or the holodeck nice photo of the cloud particles into the particle size distribution. And these can be parameterized into the model, which can save a lot of computational power by converting here to here, feeding into the model. You can immediately run the result to give you the estimation of the future weather events. And there is another side of the probe called to capture the bulk properties of the particle size distribution. So those are called the bulk property measurements. And before flying those instruments, we just need to carry out tons of the laboratory collaboration and assessment of the instrument. So we put the aircraft instrument, not the aircraft, because it's very expensive to fly the aircraft. It's like $1,000 per minute. But usually you can see one flight can last easily for like 4 hours, 5 hours. So we need to build faith on the confidence on the aircraft probe before launching it to the air. So we put everything into the wind tunnel, and artificially we make those small particles and release those particles to the cloud probe, and doing the calibration and the measurements. So here are one of the example depicting the aircraft cross-sectional view of the aircraft trajectory. So you can see during the ascending process, the particle size distribution, it's like the spectrum shrinking and the mode value is increasing. And during the decreasing, we have a reverse trend of the expanding spectrum and the decreasing of the mode values. So we use some magic, not magic, some empirical fitting, gamma size distribution, and we can compress the spectrum beam into like 3 parameters, which further compress the data volume and can be easier feed into the model. And then we can derive the 3D distribution of the cloud properties easily. And similarly, that's for the ice part, and for the liquid part, we did exactly the same, but we have the purpose not to improve the model, but to get the better estimate surface precipitation, because all the radar-based retrieval or surface precipitation, they are based on the view from downward, upward to the sky. But aircraft, they can fly very close to the cloud bottom, so we can see by joining the aircraft and the ground-based measurement, we can have a complete story of how the precipitation formed during the falling down process. And using the aircraft, we have shown that by incorporating those evolution, sorry for the noise, we can get a better estimation of the surface precipitation compared to merely based on the radar retrieval. So here are the dots represents the samples, and sorry for the noise. The blue line represents what's used to be used, and the red line represents what we present. And similar here, the dashed red line represents what's used to be used, and solid red line represents what we have improved. So you can see, no matter from what part of the cloud system, by joining the aircraft's in-situ measurement, always get a better estimation of the precipitation rate on the surface. So since we have collected enough samples regarding the cloud microphysical properties, especially the particle size distribution, we want to apply what we learned to the modeling system. But before that, we need to know exactly where and when did the mesoscale convective system start and how they evolve. So that involves the regional and global scale detection and tracking of the MCS. So the ground-based observation, they just sitting there waiting for the passage of the cloud system. So it can only take a snapshot, shadow snapshot during the passage. However, thanks to the satellite, we can exactly treat the mesoscale convective system as a continuous object. Here is an example I created using the infrared satellite product and surface precipitation estimate to track the cloud system. So you can see it starts from very small and then go upscale from the linear convection system, and then it's dissipate and finally disappear. And the precipitation and the area of the system can be well maintained. So you have this nice looking bell-shaped life cycle. So by using the satellite-based infrared cloud temperature information and the 3D radar measurements, as well as the surface precipitation product, we construct, it's not 30 years, actually update here, it's a 20-year observational MCS tracking database over the entire continental US. But again, this radar observation network is very dense over the states. We don't have such network elsewhere, even in the China or Europe. So we can only rely on the spaceborne radar, which is called the GPM Global Precipitation Measurement Mission. So since 2014, it's launched and it carries like 2 active remote sensors. One is K-band, one is KU band. So it can do the near global spaceborne scanning of the cloud system that mimics the next-ride system. Here is their spatial overlap. So you see the circles over here represents the coverage of the United States ground-based radar. So you can see it's still, even if you have a very good coverage, you still have some gaps over the mountainous regions. And the slots over here represent the GPM overpass. So in the bottom left panel, it shows the concurrent sampling of the MCS system from the GPM and the next ride. You can see, yeah, they are quite equivalent. And we did the MCS detection algorithm based on the GPM KU band radar. And we found, using the United States as the test bed. And we found like about 70% of the GPM detected MCS object are truly part of the MCS object that's detected by radar. So we have built the confidence of the GPM detection of the MCS system. And then we apply, as mentioned, the GPM has global coverage. Then we apply the GPM observation globally. And here is the spatial distribution of the MCS occurrence. So during the boreal summer in Northern Hemisphere, you can see there are several hot zones. One is Mid-American, one is Africa, and the hottest zone is here, Maritime continent. And during the boreal winter, you can see the center of the MCS hot zone is shifted to the South America. That's part of the reason that why we see like the record-breaking landslide events over here in this February, which caused, I think, more than 200 deaths. So this is for the first time the global distribution of the MCS is presented. And what I want to draw your attention is over here. So the MCS is a strong convection, but we have very high occurrence frequency over this high latitude area. So is that a surprise to you? It was a surprise to me back then. So we match the spatial occurrence of the MCS to the global warming pattern. Sorry for the noise. So here is the last century global warming anomalies. So you can see the highest increase in temperature is occurring over the high latitude, which echoes well with the severe occurrence of the MCS over there. So we took a close look at those events and found that what was a surprise to us was the high latitude MCS systems. They are very strong compared to the maritime continent one or middle latitude ones. So you can see their spatial coverage can easily exceed like 10 to the 6th power square kilometers, and also their vertical extent can easily reach like 14 kilometers. So they are equivalent to the latitude one. So that means the global change is bringing the MCS systems here northward to the polar regions. And lastly, since we have the detailed tracking, we know what we are looking at is MCS or not. And we know what the macrophysical parameterization should be like within the systems. Then we want to apply what we observe to the simulation. So there are three parts. One is using the regional climate models, one is using the global climate models, and one is focused on the natural hazard brought by the MCS. So we all know what is a model. So myself in reality is a person, but you can describe me as using different models, fashion model, anatomical models, lab models, or computer models. So why we need to care about the model? Because all models are wrong. Some are useful. So we want to make the wrong models more useful. Here was an example I conducted back in the beginning of the COVID pandemic. We use that to predict the infection, total number of infections. So you can see at a very early stage, without human interference, sorry for the noise, what we predicted, the number of cases, which is in the light blue lines, is quite in agreement with, sorry, this is the observation. This is what we predicted in orange line. It's quite in agreement with what's reported. So first thing first, before we apply the MCS information collected globally, we want to test that in the regional model. So the simulation over the continental US, the biggest challenge we are facing in the simulating the weather and climate is the dry bias over the continental US. We receive plenty of precipitation, but those precipitation cannot be well simulated through the model. And we use the machine learning techniques to examine, diagnose how the model behaves. And the technology we use was called the self-organizing map. So it's like a natural clustering method to help you cluster the weather pattern to different groups. And then you can examine the model response with respect to the different groups. So to keep the details, what we extracted was there were two types of the dominant scenario pattern. One is called the actual tropical cyclone, one is called the subtropical ridge. And the model performance has a very systematic bias. Regarding the first category, class 1 to 4, we call it the frontal, the upper is frontal, the lower is the actual tropical cyclone. So the model performance all demonstrate like a positive bias during the daytime, and nighttime it have a negative bias. However, regarding the categories 3 and 5, you see the model has only strong negative bias during the night. And regarding the transition, you see again the positive bias during the day and the transitional hour, and the negative bias during the night. So those information was first revealed to the National Severe Storm Laboratory because they are responsible for the issuance of the severe weather warning. So they are adjusting their models based on what we discovered. So since we have built some confidence in the regional climate models, we want to simulate the MCS in the global climate. So this is a part of my job back in the States at the National Lab. The Department of Energy, they dedicated themselves to the development of the energy access scale or system models, aiming to accurately simulate the water cycle globally and regionally. So one of the evaluation matrix was to accurately simulate the 3D structure of the cloud and precipitation system, both in the spatially and vertical distribution as well. But the evaluation in the global climate model has been challenging because of the coarse resolution of the GCM. So the regional climate model can have very detailed simulation because it has very high resolution with like kilometer scale. But for the global climate model, GCM, is a grid scale base spacing is like 100 kilometers. So you cannot resolve cloud or radar echoes on this scale. Here on the left is the observation at a very high resolution. I think it's a 2 kilometer resolution. However, this is what the GCM could represent. It's impossible, right? No, this is a constant that the GCM can represent. And on the right-hand side, it is what we simulated at force resolution. So it's impossible to make the apple leftmost to the rightmost comparison because there is a mismatch in the spatial resolution. So what we proposed, the solution, was to do the subgrid simulation within the large scale, within the large grid space, and make the GCM simulated cloud system comparable to the radar observation. And here is what we reviewed. On the left-hand side is the vertical distribution observed from the surface radar. And in the middle column, it is what we simulated from the cross-resolution GCM. So you can see the vertical extension is greatly reduced compared to the observation. So that is a major bias deficit of the global model, which we tried to fix. However, we can only echo top height by like less than 1 kilometer. So we found the question, we found the problem, and we passed the problem to the model development team and for them for the better improvement. And in addition to play around the coarse resolution at the large grid spacing, but implemented the subgrid simulation, another pathway is to do the high resolution simulation in the GCM. So the method I came up with was to build a nested grid spacing. So previously, the entire globe was simulated from 100 kilometer grid spacing, but then I changed that. Without the outside the regional increase, I still use the coarse resolution, but within the region, I increase the resolution. So this is called regional refinement. And the model associated with this method is called the regional refined models. And here is the consequences of with the regional refinement result. So on the upper left is observation of the total precipitation. And the upper right is the original simulation without the regional refinement, which means 1 degree equivalent to 100 kilometer spacing. So we can see a lot of details on this. But the overall pattern is dominant. We have our northeast and southwest oriented precipitation band over here. But we also have the band over here, but the intensity not comparable to the observation. Then we increase the resolution within the region of interest to 1/4 degree, which is equivalent to 25 kilometers. So you can see the pattern improves, and the high resolution, high precipitation core is better resolved, although it's still not comparable to the original observation. And then we further increase that to 1/8 degree, which is equivalent to 10 kilometers. And you can see the pattern better mimics the observation, and the strong precipitation start to be resolved. So this is quite exciting. And this method is being commercialized into the operational forecast of the United States weather phenomena recently because of the effort at it. And in addition to just increase the resolution, the other effort I made was to improve the metaphysical parameterization, because as you remember, I did a lot of aircraft in situ measurement of first-hand cloud metaphysical property. So I summarize what I observed and modifies the model inside the cloud metaphysical parameterization scheme. So this is at a quarter degree resolution. Left-hand side is the observation. The middle column is the original microphysical parameterization scheme without it. And on the right-hand side is the microphysical scheme with the improvement provided by the aircraft in situ map. So you can see the strong precipitation is better resolved. So this is too much detail in cloud physics part and also climate dynamics. So I will skip. But just for you to know, there are two pathways. One is to improve the resolution, and the other is improve the representation of the physics precise within the cloud. So both are proved successful. And then I want to look at how the extreme weather events, for example, the hail and the tornado, they are represented, they are simulated within MCS. So here is a hail example of the hailstones. And this is the damage it could bring. It can just make a lot of holes on the roof and damage your cars. And on the right-hand side is a panel there showing the tornado formation. And for tornado, it's more troublesome compared to the hail. To the hail, you just lose money, that's it. But for tornado, you lose life and you lose the entire building. Here is an example of the December 10th Kentucky tornado. So the entire town, several towns were wiped off from the map. You can see the ruins after the overpass of the tornado. So this tornado was very dangerous and caused a lot of economic loss and deaths there. But it was very difficult to predict. Here is a spatial and it's a temporal monthly distribution of the tornado occurrence. So you can refer to the red bars over here. So in December, has a minimum occurrence of the entire year. But these events, hundreds of events, tornado events occurred in December. So which went against the people's general realization of the tornado occurrence. So people was not prepared. That explains the tremendous damage. So the scientific question we want to pose, hi Josh, how much time do I have?
Hi Jingyu, you can just proceed. I think we still have 20 minutes, so you can just proceed as usual. Okay. Yeah, don't worry.
Okay. So we want to simulate the current tornado and hail events, but also we want to know what those events will become more severe in the future climate change scenario. To achieve that goal, we just use the current synoptical background and overlay with the future CMAP6 projection of the climate perturbation. The CMAP is in the comparison project of the different models. So currently, the weather forecast model will focus on the lead time of several weeks, several months, that's most season to sub-season forecast, or several days, several hours. But the CMAPs, they look at the climate projection in 2050 or 2100. So they want to see how the climate overall will change in the middle of the century or by the end of the century. So we extracted the CMAP synthesized projection of the climate scenario to the current synoptic background. And then we come up with the future synoptic background. And we want to, in this background, we want to throw in the tornado occurrence and see how the tornado and hail will evolve in the future scenario. So here is for the simulation of the hail. On the left-hand side is the observation of the hailstorm over a certain events. And the middle column shows what we simulated using our current synoptic background, the occurrence of the hail events. On the right-hand side is what we use, the future synoptic background, the occurrence of the hail. what we found that is the occurrence of severe hail, that is hailstone size greater than 2 inches, will be significantly increased in the future. And here are the microphysical properties associated with the, this change. Try to explain that. And here is a schematic plot showing why we believe so. So here is the current, in the current climate scenarios, what the MCS would be like. So a lot of hailstones, updraft bring up the hailstone to the upper layer troposphere, and during the updraft size, the hailstone size just keep growing, and they collect the supercool liquid water. And if the updraft cannot hold the hailstones any longer, they will fall out, causing the damage on the surface. However, in the future scenario, we found that the updraft will become much stronger. So that means the transport of the hailstone, the lifting of the hailstone will be much stronger. The hail mass flux will be stronger. So that means the hailstone will be pushed further upward to the lower troposphere, and also we will have a higher chance to collect the supercool liquid water during the pathway. So that means they can easily grow bigger. Meanwhile, we found that the water collection layer of the hail growth is also become deeper in the future. So that means the hailstone, the higher occurrence of severe hail will be more likely in the future because of the strong updraft and the deeper layer water collection zone. This is quite severe, 80% in large hail and 45% in highly precipitation. So again, I want to emphasize that this is not a one case. I'm showing one case just for demonstration purpose. We have simulated this continuously for 3 years, and this trend is proved basically for every single case. So it's quite scary, not for us, but for the United States fellows there. The 80% increase in large hail. How could you prepare for this thing? And also, for hail, it could be very troublesome, but for tornado, it could be even worse. Because the urban expansion, we have a lot of the skyscrapers popping up all around the globe, and the dynamic effect of the skyscrapers, they will serve as a blockage of the airflow, which will initiate carbon vortex vortex on the downward side of the building. So that increases the probability of tornado occurrence. Here is an example. The upper panel shows with the city, and the lower panel is the city, and to see how the tornado would form. And the left column shows the parameter we call the streamwise vorticity direction. And on the right-hand side, right-hand panel, it shows the significant tornado parameters. So both values indicate the higher value, both values, the higher chance you have tornado. So with the city, you can see the tornado potential is very large compared to without the city. So the presence of the city is diverging, is changing the circulation pattern overall. So we will see more tornado occurrence in the future. This is not related to the global warming, but related to the human change of the land use. Here is a schematic diagram showing how this could occur. So with the city, it can heat the urban area faster and build the thermal contrast, which can rotate the air tube. However, without the city, we don't have such strong contrast of thermal. So the rotation of the tube will be much lower. Here is a schematic diagram showing the effect of the city. So you can see the several contrasts will help the rotating field that form the tornado later. So, but the urbanization it's going on everywhere. It's exponentially, although the urbanized area grows. So we will expect to see more tornado occurrence overall over the entire globe, which is the size of climate change. We will have a higher chance of hail. Urbanization will use more tornado occurrence. So we will suffer for the rest of the future. And here is a quick summary. So the multi-platform observation from the satellite, from the ground base, and aircraft in situ observation or MCS, we can have a very first-hand and most accurate in-cloud measurements of the model evaluation. We can use those information. We can get the retrieval of cloud ice and liquid phase property retrievals, and also we can have, based on the satellite, we can review the global distribution of the MCS for the first time. And we try to use the information we obtained from multiple platform observation to the global and regional climate simulations. And we have found that the improvement is very prominent. And that could help our understanding of the not only the understanding, but also the simulation, operational simulation of the MCS, because the MCS is a major troublemaker that bring the heavy precipitation, the hail, and the tornadoes. So those are the publications I have related to the topic, and some extra work I want to share with you. One is the pandemic related recession in the aviation industry. What the climatic effect you have. So when the aircraft flies through the sky, it's usually the contrail behind. So those contrails they are transparent to the shortwave radiation, but they can block the longwave radiation. So it have an overall warming effect. Here is in the bottom panel, it shows the global aviation density before the pandemic, during the pandemic. You can see a great decrease. So supposedly, the decline in the aviation density could remove the part of the contrail in the sky, so which can reduce the global warming a little. So this work is under review, and we did find that the global warming is because of the removal of aircraft in the sky. And sorry, this is another work related to the China flood. So this is already published in Science Bulletin. So here is the global, no, not global, the Chinese wheat production area. So you can see majority of the wheat production takes place over the North China Plain. And during the month of June, we have a severe fire carbon emission. So this region, the monthly emission took about 80% of the entire nation. So what happened there was farmers left the harvest residual on site and destroy them. So it will leave some signatures on the fire carbon emission. And here is the true color image from the satellite. You can see the red dots represent the fire points, and the gray shading represents the presence of the smoke. However, this could have some profound impact on the Henan flood last, I think, last July, because the Chinese government they put a very strong push to the banning of the straw burning in recent 3 years. So the abrupt removal of the PM 2.5 and aerosols could surprise the efficiency of the precipitation process. So which is partially responsible for the heavy flood That's once in 1,000-year flood events back in Henan, Zhengzhou. And here are some work that I'm working on over my new position in Singapore. One is the anthropogenic impact on the urban climates, microclimate system. One example I want to show is the green roof that could regulate, mitigate the urban heat island effect. And another interest focus that I'm working on is the outlook of the future climate projection. As I mentioned, the CMAP, we have the projection of the climate overall in the middle of the century and the end of the century. But over Singapore, because we have very small spatial coverage, we cannot fully rely on the CMAP projection because it's conducted at a great scale of 100 by 100 kilometers. It's basically useless for us because we are just a point. So I plan to build the regional refined modeling system over Singapore and to see what we can perform here and what extreme events, for example, heavy precipitation, flooding, like in the future. And last is the downscaling. It's also related. And I strongly encourage you to read the newly released IPCC Intergovernmental Panel on Climate Change 6th assessment report. So each of them, like you can read the short version, like 40 pages. If you want to read the complete report, it's usually like 3,000 pages. But you can learn a lot to see the job opportunities, the emerging research topic from those assessment reports. And personally, I'm heavily involved in the World Meteorological Organization training systems. So if you are interested, me, and I can offer the chance to attend the international seminar. And that's all my talk. Thank you. I think I'm fine.
Yeah, thank you very much, Jingyu, for very informative talks. I think all the audience have gained substantial new knowledge from your talk. Before we move on to the Q&A session, we will have a group photo session. So, Mr. Roel, may I request you to give the instructions for the group photo for today's seminar?
Yeah, okay.
Yeah. Jingyu, so we have a group photo, so on his mark. Thank you.
Okay, this way.
Okay.
Yeah.
Okay, so good morning to everyone. May I request everyone to open the camera for the group photo and smile. So wait for some people. Hello.
Hello, Roel.
Yep. So
yeah,
give me 5 seconds.
Yeah. So on your mark. Thank you.
Okay. So everybody ready? There are some people wait for a while. Another 3 minutes. Sorry, 3 seconds. Okay, so ready. So in count of 3, smile. Okay, smile. 1, 2, 3. Hold on. Okay, thank you.
Yeah. Thank you, Mr. Roel, for being a very reliable photographer as always. It's been a while, but thank you very much. So with this, before we move on to the Q&A session, just to share with you a little bit, Jingyu. So actually, I was very excited when you show all of this, since climate change has been one of the key focus of our water engineering program. So, and then we also have Professor Sangam, who is on the top 2% of scientists in the topic of climate change. So a lot of students here, both master and PhD, have integrated climate change in their research. So look forward to, very exciting interactions. So with this, I will now open the floors to a Q&A session. So maybe I invite Mr. Saurabh Casey, who's also one of our PhD students. If you have any reflections or questions for Dr. GU. Saurabh, is it okay? Saurabh, thank you.
Yeah, thank you, Dr. Log. I do not have any questions right now. Sorry for that. You can continue. I do not have any questions right now. Thank you. Okay, thank you.
Okay, so how about Mr. Shala? Mr. Shala is also one of our PhD students who using climate change for her research. Ms. Shala, are you there?
Hi, Professor. Thank you so much. Thank you, Professor, for sharing the lecture. It was really inspiring for us WAM students here, because I think Dr. Luke, there was no one applying for that model here in WAM, so that would be a good venue for the upcoming WAM students here. So for now, I don't have any questions. Professor.
Yeah, thank you. Thank you very much. Yeah, thank you very much, Shala. Yeah, actually, I think that the research Dr. GU has shared is actually very, I would say, down to earth. I think it's quite amazing to see that you actually ride on an aircraft to do your PhD. Yeah. So may I ask, what is, did you have a rough estimate of the size of the funding for that particular project? I assume that your PhD is part of the project, is it, GU?
Yeah, it is.
Yeah.
It was.
So it's funded by the American government?
It's a joint experiment, central joint experiment by Department of Energy and NASA.
Yeah. And it's quite amazing that when you lost an aircraft, they can just basically give you a new one. So that's quite amazing. So maybe I will start first with one very simple question, GU. So I see that initially you started your research in the United States, then later on you tried to apply the same paradigm in China, and now exploring in Singapore. So can you just please maybe very short to see what are the main kind of difference when you try the same approach across 3 different geographical regions?
Yeah, the biggest challenge that I'm facing now is previously the continental US, you can only use the atmospheric model only, decoupled from the ocean. But here, you cannot do the decoupled model. I did some experiment. The result is too awful to share. We have to consider the oceanic airflow. So that is the biggest difference. I have to change from atmospheric only model to atmospheric ocean land accompanying model. So that's very.
So it means that in the US, the atmospheric was more of a driving force, whereas you apply in there are other factors that could have erupted your model, isn't it? Especially in terms of accuracy.
Yes.
Wow.
In the States, you have boundary, but you have the mountain on the west side, the Rocky Mountain, and you have the Appalachian Mountain on the east side. So the continent itself is quite isolated. But here, you cannot make that assumption.
Yeah, do you think the matter of scale is actually important, since Singapore, I would say that it falls within only one cell, right? Whereas in China and United States, the resolution, the spatial resolution. So can you give a small comment on the effect of scaling in this kind of global and regional scale model?
Yes, it's very useful to use the coarse resolution global model because it's so large. What the biggest concern when you do the modeling is the computational power. If you use the global high resolution model, you are looking at several million computer hours per 1 day simulation. That's really costly. But if you coarse the resolution to 100 100 scales, you can save a lot of computational power. But you can still look at for example, the large scale circulation pattern, budget. Those are quite uniform. So, but the global model, you cannot see the details. You cannot resolve the details. For example, the heavy precipitation, the occurrence of hail and tornadoes, extreme flood. You cannot see that. So that's the necessity of joining the global model and the regional model. Sorry for the noise.
Yeah. Okay, GU, maybe the one final small question. So in case, like I'm also a modeler myself, but the model that I have used is very small scale, either a basin or district level, where we deal with urban. So this is the first time that I had the chance to look at a mesoscale model. So for, would you call this is a process-based model, or is it a data-driven model, or it's a combination of both?
It's process-based model. It's a physics-based model.
A physics-based model. But I see that sometimes that at one point you mentioned the machine learning. I think at that point is where the knowledge of the process, the physical process, has not been made substantially enough, isn't it? And then we have to use the machine learning.
The machine learning. Yeah, the machine learning is starting to replace the empirical modeling part, empirical modeling component, because empirical, if you change to other places, the data you put will vary a lot. But the machine learning has the ability to adjust itself.
Yeah, true. So because because the physical are on empirical, right? And then empirical are obviously prone to localization. I saw one hand raised. Sanjeev, please unmute yourself and ask a question to Dr. GU. Thank you.
Thank you, Dr. Locke. Thank you, professors, for such a comprehensive presentation. Actually, I didn't have any questions, but I was just wondering about the adaptation strategies to cope with the impact of tornado and hailstorms. So for example, if there are high occurrence of flood, we can build a reservoir. For landslide, we can have afforestation, and also for tornado and hailstorms. So what could be the adaptation strategy? So actually, we are from the country where these kind of problems are very few or also no. So I want to know about this. Thank you so much.
The only solution is you immigrate to another country outside the states. Because we are doomed. We are doomed. The higher occurrence of severe hail and the more occurrence of tornado, we are doomed. So that's the reason why the United States puts so much effort to mitigate, to lead the carbon neutrality effort, to reduce, to urge every single country to reduce the carbon emission. That's the reason. Because it is the most vulnerable to the climate change. So anything will be magnified over the continental US. As I mentioned, the two mountains makes the continental US isolated place. So it has a very strong feedback on the climate change. So just for you to know, last year, after the Kentucky tornado events, the US Council, they just gave $50 billion to the National Weather Service to improve the forecast and the prediction. Just for you to know.
Yeah.
Thank you, Professor.
So we are pretty much in demand, right, GU? Our Earth scientists.
Lots of job opportunities.
Okay. I think time is around 12. So may I invite Professor Sangam, our head of department here, to give a closing remark. Professor Sangam. Hello, Professor Sangam. I think he's not available at the moment. So I think again, so thank you very much, Dr. Wang, GU, so for coming forward with us today. I think this is our very first, actually this is the second step already, because following up from our last interactions in Singapore. And I'm really looking forward for more collaborations with you and also NIE team, NTU team in the future in choice supervision of students and publications of scientific research. So with this, again, thank you very much, everyone, for joining. And then I wish everyone a pleasant day ahead. Thanks to you for
Thank you.
coming out.
Thank you.
Okay,
Thank you.
bye-bye, everyone. Have a nice day.